Welcome to our deep dive into the history of quantum physics. It's a pretty fascinating journey, and we're going to, really try to uncover how physicists went from thinking they knew it all to, to facing a reality that basically just defied common sense.
You know what's interesting to me?
Yeah.
It's that we're starting at this time, the late 19th century, when, a lot of physicists actually thought they were so close to fully understanding, like explaining the whole physical world.
Yeah.
They were brimming with this like scientific confidence.
Right.
And they had absolutely no clue. They were about to trip and fall headfirst into this revolution that would just shatter their, classic worldview.
It's amazing how sometimes, being on the edge of a big discovery can actually make you like blind to what's right in front of you.
Yeah.
So where do we even start with like a story as massive as this quantum revolution?
Well, I think we have to start with, the birth of the quantum itself.
Okay.
With this German physicist, Max Planck, and his struggles to understand, something called black body radiation.
Black body radiation. Can you break that down a bit?
Sure. So imagine like an object. It absorbs all light, no reflection at all. Hence the name black body. Now, heat this object up, and it starts to glow, and it emits light across like a whole spectrum of colors.
Okay.
Like picture, I don't know, a blacksmith's forge.
Okay. Yeah, I get that. But what was the problem with this? It seems pretty straightforward.
Yeah, so the problem is that classical physics, the physics that had worked for, centuries, it just couldn't explain what they were seeing. It predicted that the energy coming from this black body, it would just become infinite at high frequencies.
Well, that doesn't make sense.
Exactly. It's an absurdity. They called it the ultraviolet catastrophe.
Okay.
So this pointed to a big problem in like our basic understanding of energy.
So how did Planck solve this catastrophe?
Well, Planck, he found a way to make the math work, but it required a really radical assumption.
Okay.
He said that energy, it wasn't continuous. It came in these little packets. He called them quanta.
Yeah.
Like tiny little bundles of energy.
So that was a pretty big shift, right?
Oh, yeah. Huge.
From the way they were thinking about energy before? Did Planck himself, did he get what he'd found?
It's funny. Even Planck, at first, he thought it was just a mathematical trick. Just a way to fit the theory to what they were seeing.
Right.
It's like he found this fundamental truth about the universe.
Right.
But didn't really grasp,
Yeah. The enormity of it.
Yeah.
Yeah.
It kind of makes you think how many other like revolutionary ideas are just out there.
Yeah.
Hidden in plain sight.
Right under our noses. So Planck, he sort of set the stage.
Right.
But he wasn't the one to take it, to really push things forward.
Yeah, the story really picks up when we bring in another giant of physics, Albert Einstein.
Oh, Einstein. I mean, who hasn't heard of Einstein, right?
Exactly.
But how does he fit into all of this quantum puzzle?
So in 1905, a year now known as Einstein's Annus Mirabilis, he tackled this phenomenon called the photoelectric effect.
Yeah, okay.
Basically, it's how shining light on a metal can cause it to, emit electrons.
Right, yeah. I vaguely remember that from school.
So classical physics, once again, it just couldn't explain why the energy of these electrons depended on the frequency of the light.
Right.
Not the intensity.
Yeah.
It was a puzzle. Nobody could figure it out.
Yeah. So how did Einstein, crack the code?
So he took Planck's idea, this quantized energy thing.
Right.
And applied it to light itself.
Okay.
He said, look, light, it's not just a wave like everyone thought. It also comes in, you guessed it, these little packets of energy.
Quanta.
Exactly, which we now call photons.
So light, this thing that's so fundamental to how we understand the universe, it has this dual nature. Yeah.
It's a wave and a particle.
It was a radical idea, a huge shift in how we thought about light.
Yeah, that's a lot to take in.
It is.
But this was just one of Einstein's breakthroughs this year.
Oh, absolutely.
His miracle year, as they call it.
In 1905, he also published his doctoral thesis. He proposed this new way to figure out how big atoms are, their dimensions. And then there's his paper on Brownian motion.
Right.
That's the random, jittery movement of, particles.
Right, like dust particles in a beam of light, right.
Exactly.
Yeah.
And it's fascinating?
Go on.
All of these, they all point to this, deeper, interconnected reality that classical physics just it couldn't explain.
Yeah, that's a great point. It shows how, like, scientific progress, it's not always, a straight line.
Right.
Sometimes it takes these seemingly, like, unrelated discoveries to reveal some deeper truth that's been there all along.
Exactly. But for this deep dive, let's shift gears a little bit. Focus on another key figure, Niels Bohr. Okay.
A Danish physicist who took on this huge task of understanding the atom itself.
The atom.
Yeah, and he drew inspiration from the work of Ernest Rutherford.
Okay.
Who had recently, discovered the nucleus of the atom.
Yeah.
Yeah, so Rutherford's model, it's often shown like as a miniature solar system, right?
Right,
With the electrons orbiting the nucleus.
Yeah. I remember those diagrams from textbooks and stuff.
Yeah, well, that model, as revolutionary as it was, it had a big problem.
Oh.
According to classical physics, those orbiting electrons, they should be constantly losing energy, like spiraling into the nucleus.
And if that were true, the atom it would collapse.
Exactly, making atoms inherently unstable.
Right.
If that were true, atoms, and by extension, we, shouldn't exist.
So how did Bohr deal with that?
Well, he used these emerging ideas from quantum physics, building on Planck's idea of quantized energy. He suggested that electrons could only exist in very specific orbits around the nucleus. And these orbits, they weren't just random. They were determined by this quantum nature of energy.
So the electrons, they were restricted to these specific energy levels. But how did that explain why atoms were stable?
Okay, so Bohr's model said that electrons, they could jump between these orbits by absorbing or emitting light. The frequency of the light, it was directly related to the energy difference between those orbits.
Right, so atoms could only interact with light at very specific frequencies.
Exactly. And that explained why we see those distinct spectral lines when we analyze the light coming from, different elements.
Yeah, okay. So this was a pretty big win for Bohr's model.
Absolutely huge. It explained why atoms were stable and why they interacted with light in such a specific way.
Yeah. But even though it was a big step forward, Bohr's model, it had its limitations.
Right. It worked beautifully for hydrogen.
Okay.
The simplest atom. But, well, things got a lot more complicated with atoms that had more electrons.
So they needed a better, more comprehensive theory.
Exactly. One that could fully grasp this strange world of quantum mechanics.
Right. And I guess that's where we go next.
That's where the story really takes off. A new generation of physicists and the development of a truly revolutionary framework.
And that's a story for the next part of our deep dive. But before we move on, anything in particular about these early days of quantum mechanics that really stands out to you?
What strikes me is just how these pioneers, Planck, Einstein, Bohr, how they grappled with these ideas that completely upended, like, everything they thought they knew.
Yeah.
They had to let go of their classical intuitions and embrace this new reality that was just, bizarre.
Right.
And by doing that, they laid the foundation for a revolution that's still shaping our world today.
Yeah, that's a great point. It really highlights how important it is to, question what we think we know.
Absolutely.
To be open to new ways of seeing the universe.
Yeah.
Even if they seem strange or counterintuitive at first.
Right.
So let's take a break, and when we come back, we'll delve even deeper into this quantum revolution and see where it leads us.
As we really start digging into this quantum realm, we bump into these limitations of Bohr's model.
Right.
It was, a stepping stone, but it couldn't explain everything. Like, it just couldn't account for those more complex atoms.
Yeah.
The ones with more electrons beyond hydrogen.
So it sounds like the time was right for new physicists to step in, take on this challenge.
Exactly.
And this is where quantum mechanics really takes off, right? But it wasn't just one single person driving this revolution now, was it?
You got it. This whole development of quantum mechanics, it was a team effort. Yeah. Like a whole bunch of brilliant minds all working together, sometimes separately, sometimes, bouncing ideas off each other. We talked about Heisenberg and Schrödinger, but there were so many others too. Max Born, Pascal Jordan, Paul Dirac, just to name a few.
Wow, so many amazing minds all contributing to this tapestry of quantum mechanics. It must have been a pretty exciting time for physics.
Oh, absolutely. Exhilarating and maybe a little chaotic too.
Yeah, I bet. Can we unpack their contributions a bit? What about Heisenberg? What was his big contribution?
So Heisenberg, he was a real prodigy back then. In 1925, he developed something called matrix mechanics.
Matrix mechanics.
Yeah, it's like a total break from classical physics. It used matrices, these grids of numbers, to represent physical quantities.
Matrices. I have to admit that sounds pretty abstract.
Yeah, it was. It was a powerful theory, but super abstract and really dense mathematically.
Right.
Not easy to picture, or interpret physically. But then, just a year later, a completely different approach came along.
Okay.
This one was led by Erwin Schrödinger.
And this is where we get to Schrödinger and his famous equation, right?
Yeah, got it. The one that's becomes synonymous with quantum mechanics.
Yeah.
So Schrödinger, he was inspired by the work of Louis de Broglie.
Okay.
And de Broglie, he'd come up with this radical idea that matter, like electrons, could also behave like waves.
Okay, so not only did light have this dual nature,
Right.
but now particles, like electrons, they could act like waves too.
Yep. They called it matter waves.
Matter waves, wow. The universe just kept getting stranger and stranger.
It did. And Schrödinger's wave mechanics, it really embraced that strangeness. He used this idea to develop an equation. It described how particles behave, but in terms of wave functions.
Right.
These wave functions, they're like mathematical descriptions
Okay.
of the probability of finding a particle in a certain state.
So Schrödinger's wave mechanics, it sounds like a completely different thing from Heisenberg's matrix mechanics.
Oh, yeah. On the one hand, you had these abstract matrices.
Right?
And on the other, wave functions and probabilities. You can imagine the arguments, the debates
Yeah.
that were going on back then.
I bet. Like, were particles waves or matrices?
Exactly. It was a real head-scratcher.
It sounds like it. But wouldn't this whole wave-particle duality thing make the universe, completely unpredictable?
That's a question that goes right to the heart of, the philosophy behind all of this.
Yeah.
Quantum mechanics. It challenged the way they'd been thinking for centuries. But before we jump into the deep philosophical stuff,
Okay.
let's go back to this rivalry, matrix mechanics versus wave mechanics. Did one of them win out in the end?
Well, I mean, given that everyone knows Schrödinger's equation, I'm guessing his approach kind of took over.
It's not quite that simple. What they found was, and this was a real surprise, was that these two approaches, they were actually mathematically equivalent.
Really?
Yeah, two different ways of writing it down, but they led to the same predictions.
So it's like two different maps,
Yeah.
that lead to the same place.
Exactly. So even though they started off disagreeing, physicists eventually found common ground, in the math.
Yeah, okay. So the math was there, but did they all agree on what it meant?
That's where things get even more interesting. Having the math was one thing, but trying to figure out what it all meant, like
Yeah.
what it said about reality, well, that was a whole other challenge. And that led to some of the biggest, the most mind-blowing philosophical debates in the history of science.
Right. This is where we get to the really heady stuff,
Right.
the wave-particle duality, the uncertainty principle, and of course the Copenhagen interpretation. And I have to admit, even having studied some physics, this stuff still kind of makes my head spin a little.
Well, you're in good company. These concepts, they challenged everything about how we understand, reality itself. Physicists had to confront the limits of how we normally think and embrace this new picture, one that was often, well, let's just say it wasn't very intuitive.
Yeah. Let's start with the Copenhagen interpretation. It comes up a lot when we talk about quantum mechanics, but I'm not sure I really get it. What was it all about? What were its main ideas?
So the Copenhagen interpretation, it was mainly developed by Niels Bohr and Werner Heisenberg.
Okay.
It was their attempt to make sense of all this weirdness that quantum mechanics had uncovered.
Right.
And it became the dominant interpretation for most of the 20th century.
Yeah.
Although people are still, debating it and refining it today.
So how did they try to explain all the weird quantum stuff? What were the key points?
One of the main pillars is this idea of complementarity. It says that you need both wave and particle descriptions to get a complete picture. But you can't see both at the same time.
Right.
It's like trying to look at both sides of a coin at the same time. You can only see one side at once.
Yeah, that makes sense. But it still makes me wonder, what are these particles or waves? What are they actually doing when we're not looking?
Well, that gets to another key part of the Copenhagen interpretation, the role of the observer.
Okay.
What they're saying is that when we measure something, when we observe it,
Yeah.
it actually affects the system.
Really?
Yeah. It's not just passively watching. we actually play a role in determining the outcome.
Wait a minute. So you're saying that reality, like, it doesn't exist in a definite state until we measure it, that we like force the quantum world to pick a specific outcome.
Yeah, that's the mind-bending part of it all. What it suggests is that before we measure it,
Yeah.
a quantum system exists in a superposition of states.
Yeah.
It's like this blurry mix of possibilities.
Right.
And then when we measure it, it collapses into a definite state.
So it's not that we just don't know what state it's in.
Right.
It's that it's actually in all those states at the same time.
Exactly.
Whoa, okay. That's a lot to wrap my head around.
It is. It really challenges like our everyday, our normal intuition about how things work.
Yeah. And this brings us to another big part of the Copenhagen interpretation, right? The idea that quantum mechanics is probabilistic.
Exactly. And you remember, even Einstein really struggled with this idea that randomness was built into the universe. God does not play dice.
Yeah, he wasn't a fan of that. So how did the Copenhagen interpretation deal with chance, with this randomness?
They basically said, look, it's just part of how things work at the quantum level. We can't predict the specific outcome, just the probabilities. It's like chance, not some predetermined plan is what drives these quantum systems.
I bet that was hard to accept for physicists who were used to the predictability of classical physics.
You're telling me.
Yeah.
And it sparked, well, you can imagine the debates, the philosophical and scientific arguments. It was a pretty wild time.
It sounds like it. And the Copenhagen interpretation, it provided a framework.
Yeah.
But it also opened up a whole Pandora's box of philosophical questions.
Oh, absolutely.
And as we said, no one really grappled with these questions more intensely than Einstein himself.
True. His discomfort with this whole thing, with randomness, with the observer's role, it led to some of the most intellectually stimulating like conversations in history. Einstein versus Bohr. It was a real clash of titans.
Yeah, those famous debates arguing about the very nature of reality. But before we dive into those, what really struck you about the development of quantum mechanics, up to this point?
What gets me is just the sheer audacity of these physicists, They were getting results that just didn't make sense.
Yeah.
It defied all their intuition. But instead of just dismissing them, they questioned everything.
Right.
Their whole understanding of the universe. They embraced this uncertainty, this probability, this reality that seemed to like dissolve when you looked at it.
It was a revolution in science, but also in how we approach the unknown.
Yeah.
It reminds us that sometimes the biggest breakthroughs come when we let go of what we think we know.
Absolutely.
So let's take a break here,
Okay.
and when we come back, we'll dive into those epic Einstein-Bohr showdowns and see where that takes us.
Okay, so we left off talking about the Copenhagen interpretation with all its, well, pretty mind-boggling ideas, complementarity, the role of the observer, this embrace of probability. It was such a huge change from, the classical way of thinking about physics. And as we said, no one really grappled with all this more than Einstein himself. Einstein, even though he played such a big role in getting quantum mechanics off the ground, he always had doubts about the Copenhagen interpretation. He just couldn't accept that the universe was fundamentally random. God does not play dice.
Yeah, I get that. It's hard to just let go of this idea that the universe has some kind of order to it, that things happen for a reason, not just, randomly. But Einstein wasn't just, philosophically uncomfortable, right? He actually tried to like poke holes in it, didn't he?
He did. Einstein, along with two of their colleagues, Boris Podolsky and Nathan Rosen, they came up with these thought experiments to try to show what they saw as like inconsistencies and gaps in quantum mechanics. One of the most famous is the EPR paradox.
The EPR paradox, another one of those thought experiments that makes you really think,
Yeah.
about how weird the quantum world is. Can you kind of walk us through it? Like what was Einstein's point?
Okay, so the EPR paradox, it focused on this idea of entanglement.
Right.
This is where two particles, they get linked, their fates are intertwined. It doesn't even matter how far apart they are.
Okay.
Like, imagine two particles that are entangled in a way that their spins are correlated. If you measure the spin of one and you find it's, let's say, up, you instantly know the other one, even if it's, light years away, has to be down.
That's really strange. It's like they're communicating faster than light, right?
Yeah.
But didn't Einstein prove that nothing can go faster than light?
Exactly. That's the whole point of the paradox.
Hmm.
What the EPR paper was saying was that this, what Einstein called spooky action at a distance.
Yeah.
It meant that quantum mechanics was incomplete.
Hmm.
Like if you can know the state of one particle instantly, even across these huge distances,
Right.
it means that those properties, they must have been set all along. There must be some hidden variables, that are carrying this information. So you wouldn't need this instant communication.
So Einstein was basically saying there's a deeper level of reality, some hidden information that's controlling how these particles behave.
Right.
And that would mean the universe is still predictable. It was like a direct attack on the Copenhagen interpretation.
Exactly. The EPR paradox was a clever attempt to reconcile the weirdness of quantum mechanics with Einstein's belief in a deterministic universe, one where things are predetermined.
It must have sparked some pretty intense discussions.
Oh, absolutely. And Bohr, he was the main defender of the Copenhagen interpretation. He really went head-to-head with Einstein on this.
I'm curious, how did Bohr respond to this? How did he defend this idea that particles could influence each other instantly without breaking the rules of relativity?
Okay, so Bohr, he argued that these entangled particles, they're not really separate. They're part of a single quantum system, even though they might be far apart.
Right.
When you measure one, you're not influencing the other one directly.
Okay.
You're revealing something about the whole system. It's like they're two sides of the same coin. They're connected no matter how far apart they are.
Okay, that's a subtle difference, but I think I see what you're saying. So this spooky action at a distance, it's not really action at a distance. It's just this weird connection, this non-locality that's built into quantum systems. But did they ever get past just, arguing about it? Was there any way to actually test who was right?
Well, that's where the story gets even more interesting. It wasn't until the 1960s, and this was, long after Einstein had died, that a physicist named John Bell, he figured out a way to actually do an experiment. He developed what's called Bell's theorem, and it came up with these inequalities that you could actually test in a lab.
Bell's theorem, that sounds like a big deal.
It was. It took the debate from, just thought experiments to actual experiments.
Right. What did it predict?
So Bell's theorem, it basically said that if Einstein was right, if the universe was local and realistic, then the results of certain experiments, with entangled particles, they would have to follow certain rules, these inequalities.
Oh, okay.
But if quantum mechanics was right, if the universe was really non-local, then those rules would be broken.
So they just had to do the experiment and see what happened. What were the results?
The first real experiments to test Bell's inequalities, they were done in the 70s and 80s, most notably by John Clauser and Elaine Aspect. And the results, well, they were revolutionary. They showed that Bell's inequalities were broken.
Really?
Yeah. They confirmed what quantum mechanics was predicting. And it basically dealt a fatal blow to Einstein's hope for a deterministic local universe.
So after all that back and forth, after decades of debate, it was the experiments that finally proved Bohr and the Copenhagen interpretation were right. I mean, did that finally settle it?
Well, the experiments definitely show that non-locality is a real thing.
Yeah.
It's a fundamental part of the quantum world. But the debate about how to interpret quantum mechanics, well, that's still going on today. Some physicists are still looking at other interpretations, trying to make the strangeness of it all fit with our everyday experience.
Yeah.
But Bell's theorem and those experiments that confirmed it, they were a turning point.
Yeah.
They showed that non-locality is here to stay.
It's amazing that these discussions about the nature of reality, these discussions that started almost 100 years ago, they're still happening today.
I know. It shows how much of an impact quantum mechanics has had, not just on science, but on how we understand the universe and our place in it.
We've covered a lot of ground in our deep dive into the history of quantum mechanics, from Planck's first steps into this weird world to Einstein's struggle with the consequences of his own discoveries. As we wrap up, what would you say are the key takeaways for our listeners?
I think the story of quantum mechanics is a story of courage, intellectual courage. It's about questioning what you think you know, and it's about embracing the unknown, even when it seems impossible.
Yeah.
It shows us that the universe is way stranger and way more wonderful than we ever could have imagined.
Yeah.
And maybe the most important thing, it shows us the power of human curiosity, this drive to understand, the nature of reality itself.
Couldn't have said it better myself. And on that note, we've reached the end of our quantum leap through history. We hope you enjoyed the ride and that you'll keep exploring this fascinating world of quantum mechanics. There's still so much to learn, so many mysteries to solve. So until next time, keep questioning, keep exploring, and keep wondering about the universe and our place in it.